Welcome back to NE 630, Nuclear Reactor Theory. We're still on the same chapter discussing the solution of the diffusion equation. In the very early beginning, we discussed the solution in a non-multiplying medium. Then we moved on and we solved it in a multiplying medium. Then for the last two lectures, we were discussing the homogenization of the cell. So in order to solve the single velocity or single speed or one speed diffusion equation, we assume that the nuclear constants like D and sigmas are constants or are uniform, constant in space. Of course, the case where you will have a nuclear reactor, you do not have uniform distribution, let's say, for those parameters. So we have to do homogenization. So the first thing is we choose a unit cell composed of fuel plus moderator, and we homogenize, and we obtain what? We obtain an average value for the cross-section, sigma absorption effective. Now, what about if we have a cruciform shape of a control rod, for example? How we will homogenize the control rod? So this is the topic of this lecture, and hopefully by the end of this lecture, we will be done with this chapter, because we are not going to discuss the numerical solution, numerical analysis, or finite difference scheme for solving the diffusion equation. It's beyond the topics covered in this course. So we'll be moving on to the next chapter, which will discuss the neutron variation in energy in nuclear reactors. So let's start. So last time, or last couple of lectures, if you will notice, we have something like this. So we have 1, 2, 3, 4 cells, and in between those 4 cells, we used to have our cruciform control rods. So this is the control rod here. And again, in each one of those fuel assembly, we used to have fuel rods and so on. And the last lecture, or the last couple of lectures, we took one of those. Here is a one fuel element. Let's assume that take this one here and just magnify it, and we'll take imaginary volume around the fuel, and we said that this is the moderator and this is just a cell, and we call it unit cell. Then we homogenize the unit cell, and when we homogenize the unit cell, we move to a homogeneous distribution of fuel and moderator, and it has sigma absorption effective. Or something similar or familiar to this one. So now we will do the same here. So we'll homogenize everything, and we'll have a bigger cell which is equivalent to the other one, not big cell now, that has this control rod inside it. So this thickness here, or length of the control rod is L, and the length of the bigger moderator and fuel cell is M. And let's assume that this is T, the thickness. Let's assume that this is X. So this will be also X, and this will be also X, and this is X, here this is again x, and this is x, and this is x. So you will notice that this is L, and you will notice that L is just 2x plus 2t. So this is 2t. So just L will be equal to x plus 2t. If you look at x, or x plus t, sorry. 2L is 2x plus 2t. Why we are doing this? So if you want to solve, to homogenize, so the first step is to homogenize the fuel with the moderator and make this is a uniform region of fuel and moderator. This is a uniform region of fuel and moderator, a uniform region of fuel and moderator, and so on. Then we have now a control rod sitting in a uniform fuel and moderator. So this is the control rod, and this is a uniform fuel and moderator. Now we want to homogenize and to get a equivalent or effective cross-section for the absorption inside the control rod. Why? Because if you want to solve the diffusion equation, you want to be able to solve the diffusion equation uniformly with uniform coefficients in a cell like this. So you'll say here is sigma effective for moderator and fuel, and here and here and here. But now I have a cruciform control rod that I want to do what? I want to homogenize it and obtain some homogeneous coefficient, for example, for sigmas. So the first step is to homogenize the fuel moderator assembly using the same procedure as before, or some sophisticated technique. So based on the transport theory, because diffusion theory will fail near control rod. Why? Because the absorption is very high. And when we drive the diffusion equation, we neglected the absorption with respect to scattering. If you remember, in the e to the power of minus sigma total, we said that this is e to the power of minus sigma scattering, not sigma total. And we approximated this. So based on the transport theory, this will yield a model of a cruciform control rod embedded in a square cell of homogeneous fuel and moderator. So this is a cruciform control rod embedded on a cell of homogeneous of fuel and moderator. So if the length of the control blade is long, so if your L is very large compared to L, so this is the length of the control rod, and this is the diffusion coefficient, diffusion length in fuel moderator homogenized region. So if this is the homogenized region, this is the homogenized region. If your length here of this control rod is longer or larger than the diffusion length, we can consider that the penetration of the neutrons in the control rod is just one dimension. So we can get, instead of two-dimensional cruciform control rod like this, we will say it's only one dimension, so we can transform it from two-dimensional control rod to just one dimension. So how to do this is to conserve the surface to volume ratio for the cell. So we want to conserve the surface, conserve surface to volume ratio of the control rod inside the cell. So let's assume that this is here in XY direction. So this is X, this is Y, and there is a Z direction like this. Of course, this cruciform control rod goes, let's say, like this. So if we take a unit direction in the Z, 1 centimeter in the Z, and now we want to calculate the surface area for the control rod. What is the surface area? You will notice that if this is X, this length is what? is x multiplied by unit area. So what's the area here? Well, no unit length. X by 1 is x. Yes? So how many x's here? You will see. 1, 2, 3, 4, 5, 6, 7, 8. So how many x's? 8 x's multiplied by 1. So this is 8 x's. So this is 8 x's. And you will notice that also you have 8 t's. Because this is what? 2t, and 2t is 4t, and 2t and 2t is 4t. So this is 8t. So 8 x's plus 8t is how many L? Guys, 8 x's plus 8t is how many L? 8L. So this will give me 8L. The surface area is just 8L. This is not, the book just write some final form. I'm just giving you where we obtain this. Yes?
How is Lx plus t? Would that be 2L on the...
Okay, this is 2t.
Yeah.
So this one is 2t. Okay?
Okay.
So x plus 2t plus x. It is 2x plus 2t. What's 2x plus 2t is what? Is the contour rod should be 2L. Okay? 2L. I'm sorry for this mistake. 2L. And this is 2M. Okay, guys? So this is 8L. Now, what's the volume now of the cell? What's the volume of the cell? The volume of the cell will be 2L, 2M multiplied by what? No, 2M by 2M will give you what? 4M square multiplied by 1. This is 4M square. But this is the whole volume. So I have to take out of this the volume occupied by what? By the cruciform control rod. So 2M by 2M is 4M squared. I have to subtract from this the volume of this. What's the volume of this? So the volume of this is this by this. This is what? X by 2t. Yes? So this is x by 2t. X by 2t. Times what? 4. 1, 2, 3, 4. But I have here, the center one is 2t by 2t. Which is what? 4t squared. Yes, guys? So this is 2t multiplied by x multiplied by what here? By 4. So this will give me what? 8xt plus what? Okay? So instead of this, I will make it, this is 2L, yes? Yes, guys? 2L multiplied by 2T is what? 8LT. Yes? This is 2T and this is 2L. So this is 8LT. And then I have another 8LT. 4. So I have 2t multiplied by 2l is 4lt. And I have another 4lt coming from this, so 8lt. And I have to subtract this square, which is what? 40 square. So this is just the volume here. So I have to subtract from this 8lt minus is plus 50 square. So I have to conserve this surface to volume ratio. Do you know what I'm doing now? Yes? So first thing I have fuel cells, fuel assembly, a cruciform control rod. So using the technique that I did last time, I will homogenize the fuel and moderator, the fuel and moderator, fuel and moderator, fuel and moderator, homogenize everything. I get uniform now, a control rod sitting in a uniform distribution of fuel and the moderator. As if you grind the fuel and moderator and you make it something like the fuel, make it like salt and dissolve it in water, then you will fill a tank, something like barrel pipe tank. You fill it with the salt and water, which is the fuel moderator. Then you put the cruciform control rod inside. Now, if we want to transform this cruciform control rod to one dimension, yes, guys, we want to transform it from 2 dimension to y dimension. What 1 dimension? Why we want to transform it like this? The transport theory said that if your diffusion length inside the fuel and moderator region here or here or here or here is very small compared to this length of the control rod, I can consider the control rod as 1 dimension. Okay, guys? So I want to transform from 2D to something like 1D, something like either like this inside the 2M, or you can make it like this, whatever. So I have to conserve what? I cannot just say, okay, here is 2D, here is 1D. I have to conserve what? I have to conserve the surface area of the fuel, of the control rod, to the volume of the cell around it. Yes, so that I will transform it to the new thing. So this is the surface area of the control rod divided by the volume what? Volume of the cell volume. Okay, guys? Now, so what's the ratio? What's the ratio of surface area to a volume? A unit of what? Area to a volume. A unit of length. So I will call this 1 over A. I will call it what? 1 over A. So what's A now? What A? So it will be 4m square minus 8lt plus 40 square divided by 8l. So this is A. So what I did in this model, is just transform it from a 2D to a 1D. Now I will solve the diffusion equation. Negative d to phi by dx square plus sigma absorption phi of x in 1 dimension only equal to a source naught. Source naught is just a source of neutrons inside what? Inside the fuel and moderator region. Fuel moderator. And this is just the control rod. I transform it from a 2D to 1D. Then I can split this and take only, let's say, take only this region here to make a unit cell, something like this. So I will take part of the moderator and the control rod inside. So in this case, I will have, here is the control rod, and this is the fuel moderator region, and I will have, this is the A now of the distance between the moderator and the control rod, and the control rod has 2t, the thickness. So the thickness of the control rod was 2t, but the L was 2L. Then I transformed this from a 2-dimension to a 1-dimension, and I got a characteristics A for the unit cell. So this is the A for the unit cell, and this is the 2T from before. So this is the contour rod. So you will have S naught is just a uniform source of neutrons slowing down in the fuel moderator region. The fuel moderator region. So the fuel moderator region is defined from 0, x equal to 0, up to x equal to what? A. And the control rod is from x equal to A to x equal to A plus 2T. And now you have a symmetry symmetry boundary condition to solve. The symmetry boundary condition says that because of the symmetry, the flux at 0, because we have a symmetric situation, d phi by dx at x equal to 0 is just 0, meaning that the flux will be maximum somewhere here in the moderator region. So then you will use a transport boundary condition. So you cannot solve the diffusion equation inside the control rod because it's not valid there. So you will use the transport theory. So you will use a transport boundary condition. And this transport boundary condition is just the current at A over the flux at A is just equal to, the ratio between them is just equal to alpha, and alpha to be calculated from transport theory, as we cannot solve the transport theory inside the control rod. And without giving the details, it's not even the details, it's not mentioned in the book, but the book says that the transport calculation yield alpha equal to 1 over 2 E3 of 2 sigma absorption inside the control rod multiplied by the thickness of the control rod divided by 2 divided by 1 plus 3 E4 of 2 sigma absorption C of T. So what's E, E1 and E2 and E3 and so on? Did you hear before about the error function? Did you hear about the error function before? So the En is just the error, the exponential integral function, or exponential integral function, and it is defined as En as a function of g is equal to 1 to infinity multiplied by e to the power of minus gu multiplied by u to the power of minus n du. So when you integrate this with respect to u, you will eliminate u and you will have remaining g and n. This is why you have En as a function of g, and it depends on the value of n. So you will have E1, E2, E3, E4, E5 and so on. This is why we have here E3 of the degree 3 exponential function or exponential integral function of the third order and exponential integral function of the fourth order. And sigma absorption C is just the control rod absorption cross section. So from the transport calculation, what we did is we homogenized the cells, fuel and moderator. If the diffusion length is small compared to the length of the control rod, we'll transform it to a one-dimensional geometry. Then we will use the transport equation to solve the ratio between the current and the flux at x equal a at the surface of the control rod, because diffusion equation cannot solve the is not valid at control rods. Then once you get this value for G of A at phi of A, which you call it alpha, we will figure out that this alpha is just a function of the error exponential function multiplied as a function of sigma absorption of the control rod and the thickness of the control rod. So we now, once we get this, you will notice also that the flux will be just given by S naught, which is the source inside the fuel moderation region here, divided by sigma absorption multiplied by 1 minus, this is from the transport calculation, 1 minus alpha cosine x over L divided by alpha cosine A over L plus D over L sinh A over L. So we now define an effective diffusion theory cross section. So this is from the calculation of the transport theory. So we want to do something like an equivalent diffusion equation absorption cross section. Again, I told you that the diffusion equation is not valid for what? For control rod. What we are trying to do right now is we transform it from 2D to 1D. We use the transport equation to get this alpha and to get the shape of the flux and so on. And we want to transform this to get some effective cross section that can be used in a diffusion-like equation. So like diffusion equation, we need to get effective cross section from this calculation for the control rod, so we will be able to use it in the diffusion equation. So the diffusion equation itself, if you try to solve it from the beginning, it will not be valid inside a high absorber. So we use the transport equation, we homogenize, we transform it from 2D model to 1D model. We use the transport equation, we get the ratio for the current to flux at the surface of the control rod. Then once we did this, now we want to define an effective diffusion theory cross section for the control rod by requiring that the diffusion theory and the transport theory will give me the same calculation. So this is the requirement now. So we will pick up a diffusion coefficient, absorption cross section for the control rod, that if I solve the diffusion equation will give me the same solution given by the transport equation. So we now define an effective diffusion theory cross section for the control rod by requiring that the diffusion, so let me write it here. So we will define an effective diffusion theory cross section. I will write cross section as XS. Cross section for control rod by requiring that the diffusion theory and the transport theory, this is transport theory, the transport theory, diffusion theory and the transport theory calculations of neutron absorption in the control rod region will agree. So this is our goal. So how to do it? We'll just say, okay, sigma C, the control rod effective absorption cross section multiplied by the average flux multiplied by the area of the cell. We will use one, as I told you, 1 centimeter in the z direction. So if you multiply 1 centimeter by the area, this will give you what? Volume of what? Of the cell. Volume of the cell multiplied by the total number of what? Total number of absorption inside the control rod. This is effective cross section for the control rod. So this is from the diffusion calculation. Should give me JC multiplied by BC. JC is the what? Is the current. So whatever absorbed inside the control rod here is coming from the current GC that's coming to the control rod here, multiplied by what? The area. Okay? By the area, surface area of the control rod. Of course, this is area. The current is what? Number per unit. Area per second. You multiply it by what? By the area will give you the total number. So this is total number and this is total number. Just a balance equation. This is from the transfer theory. This is from what? Diffusion equation. So PC PC is just equal to B. And I will tell you what's B now. So phi average is the average what? Phi average is average what? Average flux in the fuel moderator region. How we get this? By solving the diffusion equation in what area? In the moderator region. We will get the flux. Then you will average it. Once you will average it, you will get phi. And what's the area of the cell? It's just A plus T multiplied by B, which is A plus B plus T, okay, multiplied by B. So you'll take B will be in this direction. So this will give you this area, then multiply by 1. This will give you the volume. And BC is just equal to B. And JC is equal to neutron current in the fuel moderator region. If you do this calculation, you will end up with sigma control rod effective, the effective absorption cross section in the control rod region, which is equal to BC over the area of the cell multiplied by JC divided by the flux, and this will be just 1 over A, which A, we calculated A to be what? And A was the inverse. You remember when we get the conserve the surface to what? Surface to volume ratio. This was the volume to surface ratio, the inverse, A. So this will be 1 over A multiplied by alpha that we just got from the transport calculation multiplied by the flux at A divided by the average flux. So this will be just sigma absorption divided by A multiplied by sigma absorption over alpha plus 1 over L cotangent hyperbolic of A over L all to the power of -1. I know that it's tedious. I know that it's not an easy calculation. You're not even, I'm not asking you, by the way, guys, I'm not asking about anything here more than you understand that, okay, in order to solve the diffusion equation that we have been solving for the, let's say, last 5 or 6 or maybe 10 lectures, the diffusion equation is in this form. This is the form of the diffusion equation. All what I want you to understand that the diffusion equation d by dt 1 over v multiplied by the flux equal to d nabla square phi minus sigma absorption phi plus nu sigma fission equal to source. Sorry, plus source equal to this. This diffusion equation, all what I want you to understand is the diffusion coefficient, the sigma absorption, the nu, the sigma fission. At the very early beginning, we assume single speed or single energy. But somebody will say, oh, I have this energy distribution. This is the energy, and this is f of E as a function, the distribution function for the neutron energy. This is fast, epithermal, thermal. So how you will assume that your coefficients are constant of energy? They do not depend on energy. So what we did is we will say, okay, we have sigma, let's say sigma absorption is a function of energy. All what we will do is we will give the energy variation for sigma absorption. We will multiply it by the flux as a function of energy, which is this. This is the flux. This is corresponding to the flux as a function of energy. And divide by the flux as a function of energy, dE, and you integrate from 0 to infinity, and this will give you the average absorption cross-section. The absorption cross-section, let's say for the uranium, will be something like this. Then you have the overlap resonance region, then you will have something like this. So this is sigma of E versus E. So you will get this energy variation in a functional form. Let's say this will be certain function, a e to the power of n plus a n minus 1 e n minus 1 blah blah blah. Certain polynomial. Try to fit a polynomial, you will get certain polynomial of energy. Then this is the flux of energy. Integrate sigma absorption of A multiplied by phi of A over 0 to infinity and divide by phi of E dE. If you integrate the flux over the energy, this will give you what? Energy independent flux. Yes, energy. So this is weighting. This is averaging process. So you average all parameters. As you average sigma absorption, you will also average what? D. And you will average also what? Nu. And you will average all the nuclear parameters. Then now this equation is a single speed equation for this. It's evaluated at single speed. So it's one speed diffusion equation model. Okay, guys? Now, when we solve this, we said that, okay, we are solving this in a infinite medium, non-multiplying, then finite medium, non-multiplying, and we put sources at the center, line source, point source, surface source, and so on. Then we moved on and solved this for a multiplying medium and look for the solution. But in all the solution, we assume what? D is constant in space, and sigma is constant in space. Nu and sigma fission are constant in space. But this was not the case. And one of the obvious thing, this term, the first term on your left-hand side of the equation, which is d nabla square, it was not d nabla square. Do you remember what's this one? So this was divergence what? J, and divergence of J is what? So the leakage actually was negative divergence of J. And this will be divergence, negative divergence of J. J is what? D grad what? Negative D grad phi. But negative goes with what? Was negative. So we said if D is constant, we will get D outside, and this will give us what? D nabla square. So as one of the assumptions that we try to solve and simplify, we said D is constant with respect to space. This allows us to bring it, because this is, the nabla is just what? Differentiation with respect to what? To space. So if this is a constant multiplied by a function, I will take it outside the differentiation. So this is the assumption that we did. We assume that our values, D, nu, sigma efficient, sigma absorption, are independent of space. But this is not the case. The case is we have heterogeneous reactor. And I showed you that this is the heterogeneous reactor. So we said, okay, how we will homogenize? How we will homogenize those separate fuel and separate region for the moderator and so on. So we said there is a simple way. As you average here over what? Over the energy, you will also average sigma absorption over the volume fraction. You will say that this is sigma absorption in the fuel multiplied by the volume of the fuel divided by what? Volume of the fuel plus volume of what? A moderator, and I will call this sigma average homogenized. But we said this will not work. Why will not work? Because this does not take into consideration the flux dip because of what? Self-shielding and other stuff. So we said, okay, so if you want to do it the right way, so the right way is to say sigma absorption for the heterogeneous case, to move it to be what? Sigma absorption of the fuel multiplied by the flux in the what? Average flux in the fuel multiplied by what? Volume of the fuel divided by sigma absorption in the fuel multiplied by the average flux in the fuel, volume of the fuel, plus sigma absorption in the moderator, phi average in the moderator multiplied by V in the moderator. Yes, guys? Yes? Then we solved this unit cell. We took a slab model instead of a cylindrical fuel rod. We took a slab fuel rod that was a slab like this. A slab like this. And we solved the diffusion equation in the moderator and in the what? In the fuel as a slab model. And we transformed this to what? To a homogeneous one like this. Then when we did this, we got what? We got the flux shape in the what? In the moderator as a function of x. And we got the flux shape in the fuel as a function of what? Of x. Then we average the flux in the moderator. We average the flux in what? In the fuel. And we were able to substitute here with the average flux in the fuel. Here is the average flux in the moderator. And we use the fuel and moderator and everything. And we noticed that we got this XZ or whatever. And this was what? It was like this or it was like this? No. I think it was Z or something like this. And this was called what? Thermal disadvantage coefficient. So the thermal disadvantage coefficient takes into consideration the distribution of the flux inside what? The moderator, and the distribution of the flux inside what? So this will take into consideration what? Self-shielding. Yes, self-shielding. And when we calculated this and substituted here, we said that this is the right way to do it. So if this is the right way to do it, then we got the correct D, nu, sigma efficient, sigma absorption. But now we talk about sigma absorption. Sigma absorption might be in the fuel moderator region, and it might be what? Inside the control rod region. So I have to know, understand how to homogenize the control rod. And this was the topic of this today's lecture. We said that, okay, We homogenize this, and we got a cell now that's homogeneous, fuel and moderator everywhere, and I have this corrosiform control rod, and then I said that if the diffusion length is small compared to the length of the control rod, I can transform it from 2D to 1D by conserving the ratio of the surface to volume ratio of the cell. And we calculated what's the surface ratio of the surface to volume ratio of this, and we got a parameter or a parametric distance. It's called what? A. And we use, okay, if we want to calculate an equivalent or effective absorption cross-section for the fuel, we have to match the calculation from the transfer theory and the diffusion theory so that the total number of absorption inside the fuel rod will be the same. Once we did this, we obtain a value for what? An effective cross-section of what? Inside the control rod. Then this effective cross-section for the control rod, once you try to solve this diffusion equation, if you come to a region where you have a what? A control rod, you can substitute with sigma absorption to be sigma what? Sigma absorption C, which is in control rod superscript effective, which we just calculated. Did you understand? Okay, so I will stop here, but there is the last part of the chapter, because we are going way behind now, is just calculating how to calculate the, if you have a cylindrical reactor, and sometimes you have your fuel rod, control rod like a single rod like this, or a bank. If you want to control your nuclear reactor, you will have a cylindrical reactor. You have one control rod, for example, you move it at a time, or you move bank of control rods. So if you have a bank like this versus a single control rod like this, there is two models. I will not ask you of any derivation, because again, this derivation is very complicated. So just read it to understand what's going on. So next lecture, we will be starting the new chapter about the diffusion equation. Again, also before moving, all what I want you to understand is this is just the what, the reactor, and this is the bank of control rods here. You try to use, for example, and the flux. Usually, the flux in the z direction is what? Cosine. In a cylindrical reactor is what? Cosine. So if you have a cosine reactor, if you have the control rod, let's say, very, very near to the top, you do not skew, you do not destroy your flux a lot. Then once you insert the control rod, you start what? Increasing the absorption in this region, so the flux will decrease, so you'll have a skewness for what? Move it all the way inside, you will find that you skew and destruct your flux shape. We will know from, I think, the chapter that we will talk about the kinetic equation, that if you have a disturbance in the core, like you move a control rod or you insert a control rod, if the disturbance will propagate across the core very fast, and then let's assume that you have this is the cylindrical reactor. Your flux is like this. You insert your control rod, so the flux will be what? Skewed like this. But what happens is, if the disturbance, this is called disturbance. If this disturbance, after very, very short amount of time, you insert the control rod and the flux adjusted and have the same shape now, so this means that your local disturbance will propagate and you will conserve the same shape of the flux inside the reactor. This type of reactor called neutronically tight core. If the propagation of the disturbance is not propagating very fast, and you have this skewness of the shape of the flux, this is called neutronically loose or loosely coupled core. And they are very important in the reactor kinetic calculation. So if your diffusion length is, let's say, diffusion length divided by the height of this reactor is comparable to each other, this means that the neutrons will go very rapidly inside this core, compact core, for example, so the flux distribution will return back to the normal shape. So I can, in this case, I can separate the flux as a function of x and t and make it as psi of x multiplied by time of t. So this will be a shape function that for neutronically tight core, it will not change the shape. It's a cosine no matter what you will do for neutronically tight core. And then I can solve the diffusion equation here that you see it with the equation for the delayed neutron precursors, and I will only obtain a function of what? A function of time. So it will be only one function of time, and this is called point kinetic model, that you are considering your reactor as a point and you wash out the space because the space is conserved. But if your core is not neutronically tight core and a neutronically loose core, this means that your reactor is very huge and your diffusion length with the dimension of the reactor is very small. So in this case, the neutron will not propagate. It takes long time for a neutron to propagate and to reshape the flux, the skewed flux to the original function. And in this case, I cannot write this as two separate functions here, and I have to solve the spatial kinetic model. This we'll know on lecture on time. Thank you so much.